Okay, so here's where we're at now with this searching and sorting example. We created the structures, okay? We created a random array and a random item to look for. We did the first, which is the linear search, the most simple of the search algorithms. So it's searching a random array for a random item. Then we re-randomized the array and did the bubble sort algorithm. And the bubble sort is the simplest of the sort algorithms, though it's not the most efficient. Okay? And it's certainly not the most intuitive. Then we re-randomized the array and did the selection sort. Now the selection sort is actually the more intuitive algorithm. It's the way you would probably do it naturally. But the way we wrote the selection sort algorithm, if we take a look at the last thing we wrote last week, this selection sort algorithm makes use of a few other methods. The create empty duplicate method, etc. So I'm just going to collapse those. So the selection sort algorithm uses 5 other methods to implement. But that's not the only way you can write the selection sort algorithm. So what I want you grade 12s to do right now is go in and I want you to write a second selection sort algorithm inside the sort tools class. Now, this will not be overloading because it's going to have the same parameter. So we're going to have to call it something other than just selection sort. So let's call it selection sort optimal, because this is a better version of selection sort, and it takes an integer array as a parameter. Okay? So this is a second version of the selection sort algorithm, but this one will be different than the previous one. And how it will be different is it doesn't call any other methods. So this one, all the logic resides just within the method itself. Okay? In order to do that, it has to be a little more complex. The previous selection sort algorithm, if I just open that one up, is fairly intuitive, although it calls on other methods. It creates a duplicate, an empty duplicate. While the array's not empty, it finds the lowest and removes it from the original array. It adds the lowest to the back of the duplicate array, and then it copies the duplicate onto the original array. It is fairly intuitive in its design, but it makes use of lots of method calls. So in reality, it's actually not that efficient in terms of memory usage or speed. So our selection sort optimal is going to work a little bit different and a little bit more efficiently. Okay. So here's how this selection sort optimal is coded. Let's move that down. It starts with a for loop. Okay? The for loop goes through array.length, but array.length minus 1. So it goes to the second last item in the array. It creates a lowest value equal to I. So lowest will be 0, 1, 2, 3, all the way through the array. So lowest will be set to the I value. Then it starts the second for loop. And this one goes through array.length. Okay, so now the second for loop is using the j variable to loop through array.length. And inside here, we hit an if statement. If the array at spot j is less than the array at spot j, or sorry, at spot array lowest, then lowest equals j. So this performs a swap like we did in the bubble sort, kind of, but it's not really swapping each one. It's checking to see if the array at spot j is less than the array at spot lowest. Okay? And then finally, it hits an if statement. If lowest, oops, is not equal to I, here we actually have to perform the swap algorithm again. Int temp equals array spot I, array spot I equals array spot lowest. And then finally, oops, array spot lowest equals temp. So this performs a swap. So in a lot of ways it looks very similar to the bubble sort algorithm in the sense that we're performing a swap at this point, but the logic here is slightly different. Now there's one other thing that we have to change, because at this point it looks so much like the bubble sort algorithm, and the change happens up here. J does not start at 0. J starts at I plus 1. That is an important change to make, okay? You can even put it in brackets if you want, just to sort of keep it together, okay? So that's an important change right there in the algorithm. Now, as I said before, this is a more efficient algorithm, but it's a little bit harder to follow just by looking at the algorithm itself. But before we get too deep into it, let's test it. So let's go back to here, and I'm just going to copy and paste the selection sort code, and I'm just going to call it selection sort optimal, and that's the one I'm going to call selection sort optimal. So this time when I run it, it should selection sort again, but it's using the second algorithm to do this. Not the first algorithm. Well, it's using both. It does the first one and then the second one. Okay, and it is working. It's putting it in, and I'm just going to call this selection optimal. Okay. And it is working. You can see here on the very last line, it's putting it in order from lowest to highest. Okay, so let's take a second to analyze how this algorithm actually works. Okay, so it's a trickier one to follow. And by the way, this is the kind of thing you will encounter a lot in, say, university computer science exams, is they love to give tricky algorithms and hope you can trace them. So here's the thing. We start with an array. So I'm going to draw out the array, not make it too big. Spot 0, 1, 2, 3, 4. This is called array. Let's fill it up with random numbers. 5, 7, -2, 20, 6. Okay? So here we go. We start with a variable I. And I starts at 0. The length of this array is 5. So we know it's going to go to that, but it's going to go to 5 minus 1. So it's going to go 0 to 4. It then makes a variable called lowest, and it makes it equal to I. So it's also 0. Then it makes a variable called j. Oops. And j is equal to I plus 1. So j becomes 1. And it will loop up to the length. So it'll loop up to 5. Well, 1 less than 5. Okay? It says, is the array at spot j, spot 1, less than the array at spot lowest? So is this less than that? No. So it skips that. But then it increases j by 1. So j now goes to 2. And 2 is less than 5. Okay? So is spot 2 less than array lowest? In other words, this spot. So now it's comparing spot 2 to the very first spot. And it is lowest, right? -2 is lower than 5. So now it says lowest equals j. So now lowest becomes 2, not 0 anymore. Okay? And then it continues. Now j goes up to 3. Is array spot 3 less than this one? No. So then lowest goes to 4. Is array spot 4 less than array spot lowest? No. So you can see what this inner loop has done is it has found the lowest number. It's at spot 2. So what this inner loop does right here is essentially what our other algorithm did was it finds the lowest. But then here's what it does with the lowest it swaps the lowest with the spot we're currently at. And we're currently at spot I, which is spot 0. So now what it does is it swaps the -2 to here and the 5 to here. So then it goes back and does it again. So that finds the lowest, and this part of the algorithm swaps it with the current spot. And the current spot will keep moving through the array, and it'll go all the way up to the second last one, performing that swap as it moves. So in a way, it is definitely more efficient by doing that. But when you just look at this algorithm without kind of clearly knowing that, it's harder to grasp. Whereas this one, I think, is easier to grasp when you first look at a selection sort algorithm, but it makes use of lots of other methods, so you had to do a lot more work to get it going. Whereas this one, all the logic is contained within the algorithm itself. Okay, so now you have two versions of the selection sort algorithm. We really kind of had two versions of the bubble sort algorithm as well, although we didn't write both of them. Remember, the very first time we wrote bubble sort, it was a very simple version of bubble sort that did not use the Booleans and all that. So this is already the optimal version of bubble sort. So in theory, you could get rid of the old selection sort for the new one, but I think it's still good an exercise to leave it there. Okay, so now I want to teach you your second search algorithm. We now have two sort algorithms. So now I want to teach you what's called the binary search algorithm. Okay, so to do a binary search, we need an item to search for. So I'm going to redo this line up here. I'm going to get a random item to search for. So that'll look for it. Okay. I will also randomize the array. So I'm going to take that line from up top there and re-randomize the array. Okay? Actually, I won't. I'll skip a step. The only way binary search works is if the array is already sorted. And it just so happens that it is, because we just sorted it with the selection sort algorithm. So I'm not going to re-randomize it. I'm just going to use it in its current state, which is a sorted array. Okay? So now I've got an item. So now I'm going to do these two lines, which I'm stealing up here from linear search. But I'll just put it here. This is a binary search. And that's what I'm going to call. I'm going to call the binary search, which doesn't exist yet. Okay? So here's how I'm going to implement the binary search. I'm going to look for an item. I'm going to create an item to look for. I'm then going to call on the search tools method class and use a method called binary search. And then I will display the results for the binary search for this item at this location. And we've already got code that'll take care of that in our show results method. So really all we're going to focus on is writing this method called binary search. Okay, so everyone take a second to get that in. And now we're going to go to the search tools class and write this method. Didn't write it. There we go. Create method binary search. There we go. Okay, so we're now in the search tools class. And we're going to write this method called binary search. Now here's the way binary search works. Okay, I'll just describe it to you. It's a fairly simple algorithm in terms of describing it, but it's a little more complicated in terms of how to write it. Okay? So what you have to start is you have an array, obviously, which, by the way, does not have to be the only structure that can store things to be searched, but it's the only structure that you're kind of very comfortable with at this point. And the nature of the binary search is it has to search through an array that has already been sorted, which is the case that we have. So I'm going to put some numbers, but they are going to be in ascending order. -6, -1, 0, 2, 4, 40, 100. So that's a sorted list. It's going from low to high. The way binary search works is this. Let's say I'm searching for the item 4, which happens, we know, to be in this list. Okay? The way it works is it's because it's in sorted order, it starts by looking for 4, not at the beginning of the list, but in the middle of the list. So this is a list of 7 items. So the middle of this list is here. This is the middle. And it says, is this thing 4? No, it's not 4. But what we do know is, I no longer have to search in this whole half of the list. That whole half of the list, because it is less than 4, I don't have to worry about it anymore. Now I've reduced my search area to half the size. Now I take this half of the list and I cut it in half again. I search the middle of it, which would probably be around here. Is that the 4? No. But now I know this whole half of the list I don't have to worry about because it's greater than the number I'm looking for. And now I can do it again, and sure enough, I'm going to find it. And that only took 1, 2, 3 checks to work, versus the linear search, which would have went 1, 2, 3, 4 checks. And again, this is a very small list. The binary search is extremely efficient because it halves the amount of things to look through every single time it looks. And here's how it's implemented. Okay, so to write this method, we need to keep track of 2 points in our list. The high value, so we're going to make an integer called high, and it's equal to array.length minus 1. That's the high value. The low value as well, it's equal to 0. That's the high and low of any array, because it's essentially the 2 points that we're going to separate the list by. So all arrays we know start at spot 0. All arrays will end at spot length minus 1. So we keep these 2 markers, high and low. We then implement a while loop. While low is less than or equal to high. So in other words, what's going to happen is these 2 markers on either side of the array are going to keep moving. But if they collapse on themselves, in other words, if they become the same number or they somehow pass each other, then what that means is we can't find it. So at the bottom of this loop, after the loop is finished, that's where we return -1, that we did not find it. Okay? Inside the loop, what we have to do is calculate the middle point, which I'm just going to call mid. And mid is a calculation that looks like this. It's high plus low divided by 2. That's how you calculate the middle of it. You cut the list in half. You add the high and the low together, and you half it. And then we just have a series of if statements, 3 of them. If the array at spot mid equals my item, well, then I found it. So I'll return mid. I'm done. Now I'm just going to shorten up the if statement by keeping it all on one line because it's so simple. Then I go else if the, and I'm going to slide that over so that it all lines up nice. Array at spot mid is greater than my item. Okay, well, if that's the case, then I don't need to return, but what I have to adjust is my high value. My high value equals my mid minus 1. I shift the high value over. And then the final part of this algorithm is else if the array at spot mid is less than my item, then it's the low that I change. My low equals my mid plus 1. And that's it. That's the whole algorithm. It is extremely short and simple. It's one of the most beautiful, like, if you think of code as beautiful, but it's just a simple, clean piece of logic that will work. And it's incredibly efficient. So I'm just going to show you how this would work now. I'm just going to run that code. And it's saying right there that item -7 was found at location 2, 0, 1, 2. Look at that. It worked. It found it, and it's extremely efficient in terms of how it does that. Now I'm going to run it one more time. Let's see if it works with a not found. Item 0 is found at location 6, so it found it there. Running it again. Item -12 was not found. And you can see there is no -12 in that list. So that worked really, really nicely. Okay? Now I just want to trace this algorithm again with you guys just real quick to show you how this is working. Okay? Because I described it to you. So let's do it one more time. I'm just going to draw out an array. Okay, so this is an array of 8 items. Okay? -5, -2, -1, 0, 2, 6, 40, 100. Okay. So let's say I'm searching for the item 2. 2 is the item I'm searching for. Okay, so it makes 2 variables. It makes a high variable and a low variable. And it will also, in the middle of this algorithm, calculate a midpoint. Okay? So we have high, low, and mid. That's it. Those are the only variables in play here. 3 simple integers. High is equal to length, which is 8, minus 1. So high will be 7. Low is 0. While low is less than high, well, yeah, 0 is less than 7. The mid is this plus this, so 7, divided by 2. Now we're dealing with integers. So when you divide 7 by 2, the answer is 3.5, but integers can't do 0.5. So it always truncates it to 3. It never rounds it off, it truncates it. So the answer is going to be 3 there. Okay? So it's going to start with this being the low, this being the high, and this being the mid. And it checks. Is the array at spot mid equal to my item? No. Is the array at spot mid greater than my item? No. Is it less than my item? Yes, it's less. 0 is less than 2. So now what it does is it takes the low, and it makes low into mid, which is 3, plus 1. So low becomes 4. Okay? See how it worked there? And then it goes back up the loop. Is low less than high? Yeah, 4 is less than 7. So it recalculates the midpoints. The mid is 7 plus 4, which is what? 11. 11 divided by 2 is 5. So now this is the midpoint. This is now the low point. That's no longer the mid. So the mid is now 5. Okay? And now you see what happened. It shot past the 2. But that's okay. It's going to adjust to this. It says, is the array at spot mid equal to the item? No. Is the array at spot mid greater than the item? Yes, it is. 6 is greater than 2. So now the high becomes the mid minus 1. So it takes 5, subtracts 1, and it makes the high into, sorry, not 6, into 4, right? So this is no longer 0. It's 4. And it goes back up the loop. And now it's going to recalculate the mid. So the mid is high plus low, 8, divided by 2, 4. So now the mid is 4. So now this is the mid. And now it hits the if statement. Is the array at spot mid equal to the item? Yes, it is. Return the mid. So it returns that it found the item at spot 4. So that's how the binary search works. It keeps collapsing the list down till it finds the spot. Or if it continually collapses down, these two numbers will eventually become past each other, right? So it keeps looping while it's less than or equal to high. Right now they're equal, so it kept going. But if that number got too small, the list would collapse in on itself. Because think about it, right? Low would have been recalculated and stuff like that, so it keeps shifting the values around, okay? It is an incredibly efficient algorithm. But we can actually write this algorithm one other way. And that's what we're going to do next. We're going to write a second version, a public static int binary search optimal with the integer array. So we're going to write this algorithm one more time. And it's almost identical to the one above with a slight difference. Okay? It has one line. We return recursive binary search. In the whoops, I forgot the item. Int item. For the item in the array. And we need two more parameters, 0 and array.length -1. Okay, so let me zoom in on that so you guys can see what I've been doing there. Okay, so this is going to make a call to another method that we're going to write that's recursive. So the whole idea here was, what I wanted to show you about the binary search is it can be done recursively. So it's a throwback to our first unit. So we don't know that when we just call binary search optimal. When we call binary search optimal, we're just searching for an item in an array. But hidden within that is a recursive method. And recursion is often done that way. Recursion is hidden within a class using what's called, this is actually called a wrapper method. Doesn't mean it like, goes out with Rihanna or anything like that. It just means that this method is hiding the fact that recursion is taking place. The reason we're going to then also send two other parameters are because of the way the recursion works. Okay? Now this is an extremely small method. Like any recursive method, it's going to be very simple to write. But let's do this. It will be a private method. Okay? So recursive search binary, a recursive binary search. And we're going to rename the two parameters instead of I and I0 as low and high. Okay? So recursive binary search will take the item, the array, a low, and a high variable. And here's how it's coded. It's like 5 lines. If low is less than or equal to high, hit this if statement. Otherwise, return -1. It's not found. Okay, so it starts with an if statement. If low is less than or equal to high, do something. It calculates the midpoint, like it did in the previous algorithm. But this time I'm going to use a slightly more efficient calculation of midpoint. The one I previously showed you actually has a potential for a once in a very rare case, but there is an error possibility. And it was actually one of my former students who's now a master's student at the U of M studying searching and sorting in a master's thesis that told me, no, this is the better way to write it. And so I am listening to current research. Plus high minus low divided by 2. So this, believe it or not, is actually a more efficient calculation of the midpoint. High plus bracket high minus low divided by 2. And then we hit our if statement. If the array at spot mid is greater than the item, I return recursive binary search for the, okay, let me pull back here a bit. Okay, so this is where the recursion takes place. But what I do here is instead of putting high right there, I put mid -1. Okay? And I'm actually going to move that down a line just so it shows like that. Just just for space efficiency. Else if the array at spot mid is less than the item, I return recursive binary search for the item in the array. But this time the variable I change is low. Low becomes mid plus 1. And then finally I just have the else. I return the mid. And that is it. That is the entire recursive binary search algorithm. It uses a similar logic to the previous one, but by doing it recursively, it actually is even more efficient. Now, I'm not going to trace this one with you guys. It is a bit complicated to trace, but it is incredible to look at sort of the efficiency of this. Now I'm going to just move these up just to save space. Because that's it. That's the whole algorithm right there. As simple as it is. Okay? It's just that many few lines of code to actually get working. Okay? But you can compare these two, and again, this is some pretty high-end coding here. This is often looked at second-year university level computer science courses. The efficiency of search algorithms, and glad to share that with you guys. But we should test it. We didn't test this recursive binary search. So I'm going to run all this binary search code again, but this will be binary search optimal, and that's the one I'll call binary search optimal. Okay? And run that code. Yep. So it says minus 10 was found at location 1, and there it is, right at spot 1. And that's binary optimal. Okay, so here's what we know now. In our sort tools class, we have 3 sort algorithms. The bubble sort, the selection sort, and an optimal version of the selection sort algorithm. In our search tools class, we have as well 3 algorithms. A linear search, and a binary search, and a more optimal version of the binary search. So really we have 2 sorts and 2 searches, but we have a more optimized version of the second sort and the second search. We also have a few private methods. The search tools class has a recursive private method, which is hidden by its wrapper method. The sort tools class has a few utility private methods that are used by the selection sort algorithm to just make it work and make the logic broken up a bit more. Okay? We ran all of this through a driver program that drives all our code to test it all in main that runs the linear, the selection, the binary, etc. Okay? And that's where this example ends. So that's the 2 sorts and the 2 searches that I wanted you guys to get out of this, and that will be worth points if you turn in your example right now as is. For extra points, I'm now also going to write a few other searching and sorting algorithms tomorrow that are optional. You don't have to do them, okay? If you want to, you can. I'm going to record those so that those are on the video as well. But a few other algorithms that are just a few more sorts and searches include some that are pretty a little more advanced. But I just want to finish up a little piece of the presentation that goes over this just with you guys just to wrap today. So this is in the notes on the binary search. Okay, so the caveat with the binary search is, as I said, it only works on a sorted list, okay, using a divide and conquer technique, okay? By examining the middle of the list, if the item is the one you're looking for, you're done. And then whether it's low or high, it will adjust the search criteria until it finds the item or until low or high collapse on each other, which means that the item's not in the list. Okay? So in the code, I have examples of this in play that I did on the projector as well. So it can start in the middle and it can keep dividing the list in half and in half. It is extremely efficient. Here's some stats for you. In an array of 100 elements, if they have an array of 100 different values, it would take no more than 8 possible checks to find it. Now think of that compared to the linear search. What would be the worst case scenario in the linear search would be 100 checks. So this is significantly more efficient, but wait, let me up this again. If we had 1,000,000 elements to look through, it would take no more than 20 checks to find the item we're looking for. Versus the linear search, which would be 1,000,000 checks. Now, let me take it one step higher. If we had to search the entire world's population, no more than 40 checks would have to be done using the binary search. This is a lot more efficient. But what was the initial criteria that makes it a little bit tricky? Is that it has to be sorted. So although the binary search is an extremely efficient algorithm, it relies on the list being already sorted. Okay? The code's in the notes. You can see it there. Okay? It also has the example of the recursive binary search in the notes as well. Okay? So there's all kinds of stuff in play here, right? Like in terms of efficiency. Efficiency of an algorithm for sure deals with speed, but it could also deal with things like preconditions, like that it has to be sorted, or space, that certain algorithms take up or use more space. Okay, and we'll wrap that for today.